Students who are new to fluid mechanics often confuse boundary layer separation with boundary layer transition to turbulence. Now these are entirely different phenomena, nevertheless they often occur at the same time, and so here I want to show why they are different and also why they often occur at the same time. Here are 3 photographs taken from Van Dyck's album A Fluid Motion. The first of them is at low Reynolds number. This is the flow around a cylinder, and we see flow separation at these 2 points, such that the flow behind the cylinder is recirculating. But note that this recirculation flow is definitely laminar, as is the flow in the non-recirculating part. So this is an example of boundary layer separation without transition to turbulence. In the picture on the right, we have a flow from left to right over a curved body. Here we see that the flow remains attached along the entire body, but by looking at the smoke visualization we see that the boundary layer is turbulent. So this is an example of transition to turbulence in a boundary layer without separation. The picture in the middle is of a flow again from left to right around a sphere. Here we can see boundary layer separation at this point, followed very quickly downstream by instabilities that then lead to turbulence. So this is an example of separation with transition to turbulence. And I hope that these pictures demonstrate that you can have separation without transition on the left, transition without separation on the right, but that often you get separation with transition, and it's that middle one I want to focus on next. To do that, we will go back to considering the velocity profile in a boundary layer as the adverse pressure gradient is increased. When the pressure gradient in the streamwise direction is 0, we have the familiar Blasius velocity profile. As we increase the adverse pressure gradient, the velocity profile starts to bend in the opposite direction closer to the wall. It's a bit like combined Couette-Poiseuille flow, which we dealt with in Chapter 4. So for a very weak adverse pressure gradient, the velocity profile looks like this. For a slightly stronger adverse pressure gradient, the velocity profile looks like this. For an even stronger adverse pressure gradient, the velocity profile has 0 gradient at the wall and then moves towards the free stream. And for a strong adverse pressure gradient, the flow reverses near the wall. There are 2 main points here. Firstly, as the adverse pressure gradient increases, an inflection point appears in the velocity profile. Now the inflection point is defined as d2 vx by dy squared equals 0, and you can spot it by imagining that the red line is a road and you're driving in this direction along it. You're turning to the right at the bottom, you're turning to the left where I've drawn that arrow, and where the steering wheel goes through the center line, that's where the inflection point is, i.e. it's when you stop turning right and start turning left. And this inflection point appears at an adverse pressure gradient slightly less than that at which the flow reverses. Now unless the Reynolds number is quite small, an inflection point is unstable. That is to say that small wavy perturbations will grow around the point at which the velocity profile contains an inflection point. So in summary, these inflection points are unstable except at very low Reynolds number. Therefore adverse pressure gradients tend to cause transition to turbulence as well as flow reversal. In fact, once you have flow reversal, you usually get almost instantaneous transition to turbulence. However, transition to turbulence doesn't have to happen through an inflection point in the profile. In the picture on the right here, the boundary layer is turbulent well upstream of the top of the slope, and this is in a region with a favourable pressure gradient. In this case, therefore, the boundary layer has simply become turbulent, just as it would if it were a flat plate boundary layer, either through Tollmann-Schlichting waves or through bypass transition to turbulence, as described at the start of this chapter.